Welcome to Rolle's theorem and the mean value theorem. So in this video, I'm just going to state the theorems and maybe draw a picture and discuss the implications a little bit. In the next video, we'll actually go through the proofs for the two theorems. So Rolle's theorem says if f is continuous, on the closed interval AB. Actually, let's make that up. So on the closed interval AB and differentiable on the open interval AB, and if f of A equals f of B, then there exists C in the open interval AB such that f prime of C equals 0. Again, we'll discuss the implications for both of these in just a moment. But just a very quick picture. Essentially what we're saying is if we have a function, here's A and B, and our graph starts and ends at the same y value, is continuous between them and differentiable everywhere, then somewhere in there, the function has to turn around. It has to be a smooth turnaround since it's differentiable. And so wherever that point is, be C, and we have a derivative equal to 0 at that point. All right, the mean value theorem, we get to get rid of that f of A equaling f of P, and we slightly change the derivative we're looking for. So the mean value theorem says if f is continuous on the closed interval AB and differentiable on the open interval AB, and then there exists a C in the open interval AB such that f prime of C is equal to, this is a little more complicated, f of B minus f of A all over B minus A. So just quick comment, note that f of B minus f of A over B minus A is the average rate of change from x equals A to x equals B. Or another way of saying is this is the slope of the secant line between x equals a and x equals b. In the case of f of a equaling f of b, this is just 0. This equals 0 if f of a equals f of b. So Rolle's theorem is actually just a special case of the mean value theorem. And what this slope of the secant line is going to give us is essentially, so if we take this slope of the secant line interpretation, then we can go ahead and draw a picture. So we have our graph. Here's A and B. Maybe here is the point A, f of A, and here is the point B, f of B. And the graph does whatever it does in between. Basically, what we're saying is if we find the slope of this secant line, that this slope should match the slope of some tangent line for C. So if this is slope 1, and then this is f prime of C is our slope. There is some point between A and B where those two lines are parallel. Maybe I don't need to even write slope. So basically what we're saying is there is some C whose tangent line at x equals c is parallel to the secant line. So this is the graphical interpretation. And then if we look at our alternative interpretation, or our first way, so we'll do this one in, say, green. So if now we use the average rate of change. Or what we could also say is there is some point, right, some x value between some x value, x equals c, between A and B, such that the instantaneous rate of change at x equals c is the same as the average rate of change between x equals a and x equals b. So these are sort of two different interpretations. One, you can think of it in terms of the rate of change, average rate of change, and instantaneous rate of change. No matter what's going on, how fast you're going between A and B, at some point you have to be going precisely the same rate as the average rate of change, assuming that it's continuous, the whole interval, and differentiable on the inside. Or graphically, we can find some point whose tangent line is parallel to that secant line. All right, in the next videos, we will go ahead and go through the proofs.